So, we talked about feature reduction and dimensionality reduction, several techniques that we had, like PCA, LDA, and so on. And then we mentioned about numerosity reduction or case reduction. So, numerosity reduction is just about focusing on reducing, instead of reducing number of your features or number of columns, now we try to reduce number of rows. And we saw several methods here, right? Sampling, like for example, simple random sampling, stratified sampling, and sampling by adjusting prevalence. And then we have also some other methods, like for example, estimating data using a model. For example, let's say regression model. That is also another way, instead of just storing the full data set. So numerosity reduction is mainly about reducing your storage computation and training time when data set is, for example, very large. For example, if you have millions of rows and you want to, for example, use just only a subset of your data. And so we had simple random sampling, which could be a single sample, incremental, or average sample. So I'm just quickly reviewing these topics because I've already explained them in the previous session. If you have any questions or any confusion in any of these, you can just raise your hand or ask me in the chat. Try to check the chat every few minutes. So with simple random sampling, every data point that you have, they have the same chance of being selected. So by data point, I mean just each row. So you may take, for example, a single sample and train your model. That's just a single sample, what it means. Or you may just use incremental sampling, where we gradually increase the sample size. For example, you start with 10% of the data, and then you train your model using this 10% of data. And then you go, for example, you increase it a little bit, like for example, 20%. And then you compare the performance. If you see performance gain, you can then, for example, increase the size. If not, then it doesn't make sense to increase your sample size. We also talk about average sampling, where, for example, you average results over multiple samples. So you select several subsamples, which are each of them are obviously smaller than the whole data. So it is faster to train your model on that subsample instead of, for example, the whole data set, right? So this is faster. And then at the end, when, for example, a new case arrives, then you can just use the prediction based on the aggregation of all these models. And I'm going to explain them in the next slide. Then we also had sampling by adjusting prevalence. So this first method, simple random sampling, this is regardless of which one you do, like which of these three. In general, simple random sampling is good for when you have a data set that is large but is at least fairly uniform. So for example, you do not have imbalanced data set, and you don't have any strong class imbalance. So that is when you, for example, use simple random sampling. Then what if we have class imbalance? For example, let's say you have, let me do the examples next in the slides, but for example, just you can think of fraud detection or cases where your class labels are not balanced. For example, you have 99% of one class label, 99% of your samples belong to, for example, one class, and then 1% belongs to another class. But that 1% is actually what matters most for you. And so we cannot do, for example, simple random sampling, because if you do that, there is a chance that you do not, in your sample, you do not cover any of that 1%, right? And so we can't do simple random sampling then. That's when you do sampling by adjusting prevalence. There are different ways to do it that I'm going to explain. And then we talked about the stratified sampling. This is again when you have imbalanced data set, but you you intentionally want to keep that proportions among the classes. For example, if you have your data set 70% male, 30% female, and you want to keep that proportion, then you have to use this method, the stratified sampling. And then we discuss each of them in more detail. So with single random sampling, you just choose an object randomly. If you can imagine your data set is of size, for example, n, and so of course the subset that you select should be less than n, right? And so each object has the same probability of being chosen because this is just random. And there are two main methods, sampling without replacement or with replacement. If it's without replacement, it simply means that if you select a raw data point, you cannot select it again. So it's usually what we mean by simple random sampling. In rare cases, we also do like simple random sampling by replacement. This is but less common. And this is just when you select, for example, a data point, you can actually put it back. So there is a chance that you select that multiple times. And so this is mostly like used in theoretical analysis. Then there are several problems with this method, obviously. Most importantly, we don't know our suitable sample size. So if you have, for example, millions of rows, how do we know what is the suitable sample size? Is it like 10% of your data, 30%? Should I select, for example, 10,000 rows, 20,000 rows, 100,000 rows, and so on? So that's the most important problem. And if, for example, you select your sample too small, then your model may not capture all the patterns or may not be accurate enough. And so you may miss some important information. But if your sample is too large, then your model becomes more complex and training will be longer. So you lose the benefit of sampling. And so you can see in this figure that I explained also last week, we care about like these two factors. So there is always a trade-off. So when you increase your sample size, as you see, so the x-axis shows the percentage of cases, or your sample size. You can think of it as a sample size. So as you increase this sample size, as you see, there are two factors that are important for us. One is the error rate. So obviously we want to reduce the error rate as much as possible. And by this error, I mean the error on your test set, not on your training test, not on your training set. So this is the error on the test set. And also, we want to avoid complexity as much as possible. So we don't want to like reduce the error, but at the cost of like having a super complex model, right? So we want it's a trade-off. We want something in between. And so as like you increase this number of your samples or percentage of cases, you see that your model complexity increase like quite steadily until some point, and then at the same time your error rate is also decreasing. So up to here it's perfect. So even though the complexity is increased a little bit, but your error rate dramatically decreased, which is good. But after some point you realize that increasing the number of cases, for example, from 50% to 67%, or for example to 80%, it doesn't reduce the error rate that much. Instead, it increases the complexity a lot. So you know that this is the point that you have to stop, because it doesn't make sense to have a model that is very complex with the error rate that was quite the same as, for example, with a less complex model with using less number of data. And incremental sampling, as I mentioned before, we gradually try to increase the sample size. So for example, you train your model using 10% of the data, then you train another model using 20%, and so on. So when you increase it from, for example, 10% to 20%, so at this point you have to compare the performance and see if, for example, performance improves a lot, then we keep going. But if not, then you just halt the operation, and you just, because it doesn't make sense then to increase the cases. And so incremental sampling that you see here is just you can think of it answering the question that at which point you have to stop, for example, increasing your sample size, or for example, how much data do you actually need before your model stop improving, right? Because at some point, for example, if you increase from 50% to 67%, you may not see much increase in the performance, and then you have to halt. And this is the same concept that I explained before. As I mentioned, two things matter the most. So when you look at, for example, when you compare models, you look at two things, error rate and complexity. So as you increase your sample size, and as I mentioned, the error rate on the test set. So as you increase your sample size, your error usually goes down, and at the same time your complexity increase. But up to some point, this trade-off makes sense, that you increase the model complexity a little bit while reducing the error rate a lot. That makes sense. But after some point, if you are getting your model too complex and the error rate is not changing a lot, that means you do not see much performance gain, then you stop. And this is basically what you were seeing here. And then finally, we had average sampling, which is, again, obviously, when in general we do sampling most of the time when the data set is too large, right? So instead of building one model on all your data, because the data is so huge and it takes, for example, a lot of time and it gets more complex, so we just take several random samples. So for example, let's say your data set is thousands of rows, so you have several samples, each, for example, hundreds of rows. So they are smaller, so they are faster to train, and you train a separate model on each sample. Now, each sample is more manageable, right? And at the prediction time, when a new case arrives, then you just combine the models, and you either vote, you average. It depends on whether you do classification or regression. And sorry, so this is the whole idea. So you have, for example, several samples. These are random samples based on your data. And then you have your algorithm that is trained on different samples, which result in different models, right? Because model 1 is trained, for example, on this sample, model 2 trained on this sample, and so on. And then at the end, when the new case arrives, you just make a prediction based on all models. And those predictions are averaged or voted to just give you this final answer. And this is, as I mentioned last session, similar, for example, to ensemble methods, where you combine several models. The key idea here is that, for example, if you're combining different models, multiple models, you are reducing, for example, the error, increasing your performance. And about sampling by adjusting prevalence, I mentioned that when you have imbalanced data, basically one method to sample is sampling by adjusting prevalence. When do you do that? So because for imbalanced data, you can use a stratified sampling or this one. Now you use this if, for example, you have a highly imbalanced data. So for example, look at this example. In a biochemistry data set for predicting biological potency of chemical compounds, only 0.1% of the compounds belong to the class of highly active compounds, which is the most interesting class. And so if that's the case, can you do just simple random sampling?
No.
Why? What is the problem with doing random sampling here?
It will probably be very skewed.
Yeah, you may not cover here, right? So the data is like you have imbalanced data, right? So you have, for example, class labels, and then your samples are, for example, 99.84% belonging to inactive class label and only 0.1% belonging to the active compounds, right? So if you do random sampling, then there is a chance that in your sample, you didn't cover any of this class, right? And so you're not capturing the most important part of your data, which you need for prediction, because this is what can lead to discovery of new drugs, that 0.1% belonging to highly active compounds. Other examples include, for example, fraud detection. If you have, for example, let's say you have, or for example, in the context of fake news, if you have a data set which is highly imbalanced, let's say you want to predict fake news, and then you have 90% of your data set include true information, they are labeled as true, and only 10% or 5% or even 1% belongs to the class fake. So if you do random sampling, there is a chance that you do not cover any fake news in your sample. So then if you're not having any like fake news in your sample, how can you predict that? How can you capture those important patterns? And so that's one problem. And that's why we do, for example, sampling by adjusting prevalence, which basically says, okay, if I have this imbalanced data set, if I have, for example, 0.1% of the compounds for highly active, belonging to the class of highly active compounds and 99 point something percent inactive, what I'm going to do is that I have two options. I can either use upsampling. That means, for example, I'm just repeating, or basically you're just trying to increase your minority class. So for example, if you have only 1% of your data, let's say if only 1%, 2% of your data belongs to a specific class label which is important for you, we call it a minority class. What you can do is that you can use upsampling, which means that you repeat or you just give higher weights in your model. You give higher weights to the cases belongs to this class, or you can just downsampling, or you can also do you may see these as, for example, oversampling, undersampling. So if you hear oversampling is similar to upsampling. If you hear, for example, undersampling is basically same as downsampling. And the key idea with the downsampling is that you just reduce the number of your majority class. For example, if you have 99% is your majority class, 99% of your data belongs to class, for example, A, or for example, true news, and then only 1% belongs to class fake, right? If that's the case, you can use downsampling, that is reducing the number of cases in your majority class. So you either increase the number of your minority class cases, or you can reduce the number of majority class cases. Now, how do we know which one we have to use? So, for example, if you have let's say, very large data set, and if you have a very large data set and you care about your training cost, will you use upsampling or downsampling? Downsampling, yeah. So if you already have a huge data, and so you can, for example, ignore some, for example, data in your majority class, that's fine. But for example, as I said, the risk with downsampling is that removing removing the cases from the majority class may lose some useful pattern. But if your data set is so large, then it doesn't matter. But if your data set is smaller or your minority class is very important, then you use upsampling because you don't want to lose more data. And so last sampling method that we discussed last week was a stratified sampling. So the data set D, your data set, is partitioned into homogeneous and mutually exclusive groups called a strata. And basically it says that you just split your data into groups that we call them a strata, and then each strata or stratum, each group represent a subgroup such as a class label. So and then we can just randomly sample proportional amount from each stratum. For example, let me give you an example to better understand this. So if you let me just first tell you the objective: ensuring a representative sample, especially when the data are skewed. So if you have imbalanced data set, but you want to keep the proportion in your class labels, for example, if you have 80% of the students passed in a class and 20% failed, so a stratified sampling of, let's say, 1,000 students would include how many students passed and how many students failed if you want to preserve the original proportions. So you have 1,000 students, 80% passed, 20% failed. So what would be the stratified sampling of 1,000 students? If you have, let's say, 1,000 students, so you have a data set where your class labels are either failed or passed. And then 80% of cases belong to the pass class. That means 80% of the students pass, only 20% fail. So if you want to do a stratified sampling of 1,000 students, that would include how many students pass and how many failed.
20% fail?
Which means 200, 200 students failed, 800 passed to preserve the original proportions, right? Exactly. So we want to keep, if you care about keeping that proportion, then you use a stratified sampling. And then, okay, so far we talked about different data reduction techniques, such as feature reduction or sorry, dimensionality reduction, in which you try to reduce the number of features or reducing the number of columns, for example, in your table. For instance, one method was if you have, for example, with feature selection, right? If you have several features, you want to just select a subset of that. We also talked about case reduction or numerosity reduction. In that method, we also reduce the number of rows, for example, using sampling, right? So instead of train your model on 1 million of rows, you use a subset of your data or sample of your data. And we also talked about different types of sampling. Now, the other type is that you don't want to remove any feature. You don't want to reduce the number of feature. You also don't want to reduce the number of rows. Instead, you want to reduce the number of distinct values inside each feature. And this is very helpful if you have a feature that have too many distinct values. So your goal is just to, if you have that feature with too many distinct values, like the salary example I mentioned last session, then you can just your learning algorithm has a much larger search space, right? Because then you have a lot of distinct values. So to decrease that, to reduce that search space size, we can do value reduction or reducing the number of distinct values in each feature. And in this case, you can, of course, simplify the patterns that your algorithm need to learn, and also just to, as mentioned here, smooth out noise. That is why smoothing out noise. Why we can smooth out noise with reducing values, distinct number of values. Because if you have very fine-grained differences, like many distinct values, right, then smoothing out noise is caused by those fine-grained differences, right, help you to reduce your help you to smooth out noise if you have fine-grained differences with many distinct values. So instead of, for example, having salaries like 100, 101, 102, 110, 111, and so on, you can just reduce those distinct number of values using different methods that we are going to discuss, and that simplify the pattern that your algorithm should learn, but also smooth out the noise. Now, we have several methods, but before we know, for example, the methods that we can use for value reduction, it's important to know what type of data we are dealing with. So methods for reducing values depends on your type of attribute. So in general, we have two big type of data, nominal or categorical attributes, or we have numeric, integer, or real valued attributes and numeric values. So if we have categorical, for example, attributes, you may want to do generalization that I'm going to explain today. If we have numeric attributes, then you may want to do rounding, binning. We discussed about binning last session, and so on. So let's see first what are these different types of attributes. So first, nominal or like our categorical attributes can be either nominal or ordinal. So both are categorical, both are qualitative, and so when we talk about like these categorical nominal attributes versus ordinal, the only difference is that these ones have no order, but ordinal ones, as the name suggests, have orders. So for example, color, IDs, name of cities, IDs in case that there is no order, right? For example, student numbers or anything that doesn't have any order. So that kind of ID I mean. And so they do not have any order, but ordinal attributes, which are also categorical, they do have an order. For example, if you are, for example, talking about academic rankings, grades, customer satisfaction rating, right? So these kind of things have an order, and so they are ordinal categorical. And so in general, categorical features are referring to those features that you cannot measure them. So you cannot measure color, you cannot measure name of cities, right? You cannot measure academic rankings and so on. So if you cannot measure them, means they're qualitative, and they are qualitative and they're not they're categorical. We can also have numeric attribute. So numeric attributes are quantitative, so they are actual numbers that we can measure. They can be interval scaled or they can be ratio scaled, and here you have to be careful about the difference. So interval scaled, so in your midterm, for example, I may give you some attributes asking you defining do you have any question?
It was an accident.
Okay, no problem.
Yeah, someone else here.
Okay, so back to the slide, types of attributes. I mentioned that, for example, in your exam, in midterm, I may ask you, I may give you several features and asking you about what type they are. And then you have to mention, for example, nominal, categorical, qualitative, ordinal, for example, categorical, qualitative. If they are numeric, then you have to mention numeric, quantitative, interval scaled, or ratio scaled. Or if they are, for example, discrete and continuous, right? So for each attribute, you have to mention whether it's categorical or numeric. If it is categorical, is it nominal or ordinal? Is it qualitative or quantitative? And is it discrete or continuous? Now, about numeric values, as I mentioned, we can measure them. They are just actual numbers that we can measure them. And there are two types, interval scale and ratio scale. So interval scale, as you see here, they lack absolute 0 point. For example, temperature in Celsius or Fahrenheit. What do I mean by lacking zero, like absolute 0 point? So it means that 0 doesn't mean the absence of quantity. So for example, if you have temperature in Celsius, right? For example, 0 degrees. Does 0 degree means no temperature? No, it doesn't mean no temperature. So it just simply refers to a specific temperature. So another way to recognize this is that actually I explained this with the ratio scale. So in general, for interval scale, you have to remember that 0 doesn't mean the absence of quantity. So 0, for example, in temperature doesn't mean no temperature. However, if you have, for example, height, weight, something like that, for example, number of students, things like that, these kind of features, these are ratio scale. First of all, they're numeric because we can measure them. And second, they are ratio scale because they never fall below 0, and also 0 means none in terms of quantity. So if I tell you height is, for example, 0, it means it doesn't have any height, right? So the 0 has a real meaning. For example, if I say weight is 0 kilogram, right? That 0 kilogram is actually means no weight. 0 income means no income. But temperature 0 degrees Celsius doesn't mean no temperature, right? So that's the main difference between ratio scale and interval scale, which I realize in the past, like most students confuse these two. It depends on whether that 0 means the absence of quantity or not. If it doesn't mean absence of quantity, and if it doesn't have, for example, any meaning, then it's interval scale. But if it actually means none in terms of quantity, then like for example 0 kilogram meaning no, for example, weight, then that is ratio scale. And why do we call it ratio scale? Because, for example, let's say you say 20 kilogram versus 10 kilogram, right? Can I say 20 kilogram is twice as heavy as 10? Hello, is 20 kilogram is twice as heavy as 10? Yes, it's twice as heavy as 10. So that's ratio scale. And how about temperature? Is 20 degrees Celsius actually twice warmer than 10 degrees Celsius? This is the part you may get confused, because it may seem like bad, but you can realize it when you actually convert temperature, for example, to Kelvin. So for example, 20 degrees Celsius is, if you convert both 20 degrees Celsius and 10 degrees Celsius to Kelvin, then it will be like, for example, 293 and 290 something, so 280 something, right? And then in that case, you realize that it's not actually twice as hot. So in general, if you wanted to see if it is interval scale and ratio scale, my recommendation is to look at the meaning of 0. And so if 0 doesn't mean the absence of quantity like temperature, then it is interval scale. If it has actually meaning and 0 means no quantity, then that means ratio scale. And another distinction for the attributes, for numeric attributes, if you have numeric attributes, you should also identify whether they are discrete or continuous. So discrete attributes means that you can count them. For example, you can count number of students. You can count, for example, different colors and so on. So these are discrete values. But they are continuous if they are real valued measurements. So for example, they can take any real value within a range. So for example, height or weight, are they discrete or continuous? Height and weight, discrete. So if height is discrete, if height and weight are discrete, it means that we can count them. And there isn't like any real value within a range. So for instance, we have 170 centimeter, 170, for example, 0.1, 0.2, and so on, right? So this is actually, it can take any real value. You can even go between 170 and 170.1, right? So it can take any real value within a range. So we call them continuous. So you can just have like this line, have this, if you have, for example, height in your x-axis, then you can have like this continuous line to show the height and weight, right? So it's continuous. But if you have, for example, colors, let's say red, blue, green, pink, yellow, right? So they are discrete. You can count them, and there isn't any real value within the range of they don't have any range. And so this is the difference between discrete and continuous. Is this clear? Okay, great. So let's move to the next part. Now we have different ways to reduce values. For example, rounding and first is discretization. We can do discretization, we can do rounding, we can do generalization. So I'm going to explain each of them. Now, one of the most common value reduction technique is discretization, which means converting continuous data into discrete beans or categories. So you are just converting continuous numeric values into categories. So this is only applied to numeric data. So for example, you are grouping values into several bins. For example, instead of having exact temperatures like 18.3 degrees, 22, for example, 0.5 degrees, and so on, we can just map them to labels. We can just put them into categories like cold, warm, hot, cool, so on. And so this is actually reducing the number of distinct values in temperature feature, right? So instead of having thousands of different numbers for like temperature, now we can have just few distinct categories. So we're reducing noise, and it's also easier for the model to learn them, especially if you are using algorithm like decision trees. You will realize why later. And there are two common ways to do that, to do discretization or binning. We can do equal width binning, equal frequency, or equal depth binning, which I explained last session. So just to review, in equal width binning, you split the range into equal sized intervals. So if you recall in equal width binning, so let me so for example, if you recall, we had several values, right? For example, you have 2, let's say you have 5, 8, and let's say I already sorted these values like 10, 20, right? With equal width binning, what you were doing was actually you were finding the max and the mean, right? So you were finding the width, which was max minus mean, divided by the interval. For example, if you wanted to create, let's say, 3 intervals or 3 bins, then you divided by this, which were giving you the width of each bin. Now, does it guarantee that each bin, for example, if you have bin 1, bin 2, and so on, does it guarantee that each bin has the same number of values? No, because we are just finding the same width, that is the range for each use. So you start from the first one, and then you add the width to find the range for the first bin, and then the second bin, and then the third bin, and so on. While with the equal frequency binning or equal depth binning, you ensure that each bin has an equal number of data points. So you just basically split your data in a way that each bin has the same number of data points. For example, you say, I want each bin has, for example, two, for example, data points. So bin 1 has two data, 1 and 2. Bin 2 the same. And now because we have only 1 left, then that's okay. In this case, you can have like 3 here and 2 here. So in case that this is like odd number of values here. But if it was like 6 values, then you were fine. So let's say if you had, for example, another value 6 here, and then you had 1, 2, 3, 4, 5, 6 values, then you had like 2 values in the first bin, 2 values in the second bin, and 2 values in the third bin. This is equal frequency binning or equal depth binning, which ensure each bin has an equal number of data points. So we already explained this before. You can also find more examples in the slides of the previous lecture. This was just a recap or just for reviewing this. Now, this was about discretization. So you convert continuous data into discrete bins or categories. For example, converting temperature values into hot, warm, cold categories. Or you can do, for example, binning methods like equal width binning and equal frequency binning. And in like both of these cases, we are reducing the details or distinct number of values in a feature, right? But just in different ways. And then we have other methods, for example, rounding and generalization. So rounding is like, for example, if you have 462.4, right? You can round this to 462. How can this reduce your data? Easy, because you may have, for example, let's say 45.2, 45.1, 45.3, right? So you put all of them as 45. Or you have, for example, other numbers. So in this case, instead of 3 distinct values, you only have 1 value. And this is how you're reducing value. So this is why this is value reduction. And so one method is rounding, you can round in different ways. You can, for example, round this number. You can round this number so that it becomes 462, or just 460, or even 500. You can even round it to 500 according to what is your requirement. And then this obviously keep our data numeric. So the data is still numeric. So you're not converting, for example, numeric data into categories, right? You still have numeric data, but you're just reducing the distinct values, or you're just removing those tiny differences that may not even matter. And so one more thing I remembered I wanted to mention about the sorry, but I have to exit this first. So one more thing about discretization I just remembered. So can we consider discretization as data transformation? That is it data reduction? Is it data transformation? Is it both? We can write it in chat.
Both.
Both. We can consider both, because data transformation, because we're literally converting continuous numeric values into categories. So we can consider it also as data transformation and also data reduction, and more specifically value reduction technique. And generalization goes just one step further. So instead of just keeping your exact values, we can replace them with like broader categories. For example, let's say you have a data of, for example, different ages. So you have let me just write this. For example, let's say you have 20 years old, 24, 30, 38, and so on. So you have like these different values for the age. So we can replace them with broader categories. So for example, instead of like these exact age values, we can just use categories like young. So for example, if it falls between, for example, 20 to 30, we say this is young, right? Or if it is between 31 and 40 or 45, we can call it middle-aged, and so on, right? So instead of, for example, storing, let's say, 100 distinct values of age, we can simply use 3 or 4 categories. So this is another value reduction technique. We call it generalization, because we're just replacing that detailed data with broader categories. Can you give me another example of generalization?
Taking temperatures and making them hot, cold, chilly, whatever.
Yeah, that could be another example. Instead of keeping the exact values, we can replace them with categories, with like temperature. So any numeric data that you have, you can just use like use broader categories for that. And it's especially useful when, for example, like storing detailed values doesn't add much to your, for example, predictive power. That is, for example, you don't care about, for example, whether this young person is, for example, 20 years old or 25 or 29, right? So what you care is that this is a young person or it's a middle age. So if your detailed values do not add much to your, for example, predictive power, then it doesn't make sense. Would time be one? Okay, that's a great question. This is a great question. That was actually one of the questions I wanted to ask. So what do you think about the time? So first, think about, I wanted to ask you when I actually covered the type of features. Can you tell me what type of feature time is? And by time, I do not mean a duration. I mean, for example, 10 o'clock or 5 o'clock. What type of data is that? Discrete, continuous. Okay, so let's get back to, just to help you with this, I'm going to go back to, sorry, I have to close this, to the slide of types of attributes. So you can use these definitions here. Now, if I tell you time, and by time I do not mean duration. I don't mean, for example, 5 minutes, 10 minutes, and so on. But what I mean is, for example, 10 o'clock, or for example, I mean the clock time. Is this, first of all, is this categorical data? Is time categorical data or numeric? Numeric, obviously, is numeric and quantitative, because we can actually measure it. We can measure time, so it's measurable, and so this is numeric. Now, what type of numeric feature is this? Is this interval scale or ratio scale? So in order to understand whether it's interval scale or ratio scale, you have to think about whether time, and by time I mean 10 o'clock, I mean clock time, okay, clock time, like 8 a.m., 12 p.m., 0, right? Does 0 in the clock time have actual meaning? Does it mean like no time? Excellent, it's interval, right? Because it lack absolute 0 point. Like similar to temperature, when you say 0 degrees Celsius, it doesn't mean no temperature. When you're also saying, for example, 10 a.m. or 0, 0, like for example, sometimes we show the time with 0, which is the midnight, right? So it is midnight. It doesn't mean no time. And so this is interval scale, similar to temperature. And what if we have time as the duration? And of course, time is also continuous. Because you can just show like time in terms of like even between, for example, let's say 10 a.m. and for example 11 a.m. you can have it can take any real value within like a seconds, milliseconds, and so on, right? So this is continuous. So in numeric, interval scaled, and also continuous. Now, what if time is in terms of duration? So like 5 minutes, 10 minutes. So in that case, what would be the type of time? Is it ratio scale? Exactly, it's ratio scale, because when you say, for example, first of all, we don't have like it never fall below 0, right? So we cannot have minus in terms of duration. And also 0, right? For example, when the duration is 0, it just simply means no, for example, duration, right? So 0 duration has actually meaning. So 0 has a real meaning. So it's ratio scale. And more importantly, when you say, for example, 10 minutes in terms of duration, is exactly twice as 5 minutes. So it's also ratio scale. And so let's back here. We explain generalization. And another method for data reduction is data compression. Data compression is just about like representing your original data in a smaller or compact form. We have two ways, two main types: lossless compression or lossy compression. So lossless compression is where we can recover the exact original data. So it preserve the exact original data after decompression. But lossy compression is when we only recover an approximation. So this reconstruct only an approximation of the original data. So it throws away some information, but only keep what is most important. And in data mining techniques like, for example, dimensionality reduction and value reduction can be seen as form of compression as well. We intentionally lose some details to make learning more efficient, right? And so let me also talk about transformation. Hopefully we have time also for doing the Kahoot today. So so far we mostly focused on reducing data, right? We learned different data reduction techniques. Now, either through feature reduction, that is focusing on the features, focusing on reducing the number of features. For that, we covered several topics like PCA, LDA, feature selection, and so on. Then we talked about numerosity reduction or case reduction, where we focus on reducing the number of rows, right? And in that, we also learned about, for example, sampling, different sampling techniques like simple random sampling, stratified sampling, and then sampling by adjusting prevalence, and so on. And now we want to, and then we finally learned about value reduction through, for example, binning, discretization, generalization, and so on. Now we want to change the form of data to make data mining easier. This is called transformation. So we want to transform the data into appropriate form for data mining. And we can do, for example, feature construction. For example, when we create new features from existing ones, for example, instead of total sale and units sold, we can create average sale per item. And this new feature now may be more meaningful and more useful for our analysis. And feature selection, you can also consider feature selection also as type of data transformation, but it can also be data reduction. So it can be both. And then normalization. So in data transformation, another type is normalization. So how do we transform using normalization? We just rescale our values or attribute values to fall within a small specified range. For example, to fall between 0 1. And this is very helpful if you have different features with very different ranges. For example, if you have a data set with people information, let's say employee information, with their gender, age, income, and so on, having features like, for example, age and income with very different ranges, right? This can mislead your algorithm later, your learning algorithm. So it's better to put them into similar scale, for example, 0 to 1, minus 1 to 1, and we call this normalization. So, and this is to avoid getting your model biased in one feature, because if you keep, for example, you don't normalize this, then you have, for example, salaries, as I mentioned several times in class, ranging from, let's say, $0 to maybe $1 million, and then you have age only ranging from 1 year old to 1 year old to, for example, 100 years old. And this causes some algorithm, actually most machine learning algorithm, treating that feature as more important while it is not necessarily. And we have different techniques to do normalization that I'm going to explain. Min-max is one, then z-score normalization is another method, and finally normalization by decimal scaling. And so I'm going to explain these three, followed by discretization, which is just converting your numeric attributes into categorical attributes. So this is a formula for min-max normalization. Please do not panic, like just seeing this this formula. This is most of the time when, for example, I'm telling you to normalize values to, for example, this range 0 1, right? Then by default these are these are omitted. So I'm going to use the drawing here. Okay, so if you are going to, so this formula says your v prime or your new value will be calculated this way. So you have to deduct, you have to first find minimum and maximum, then deduct mean from your v, which is your original value, divided by max minus mean, and then multiply by this number plus your new mean. Now, if you are, for example, let's say you have income range from $12,000 to $98,000, and you want to, for example, normalize, let's say, 60,000 to, for example, this range, 0 to 1. So this is your mean, right? So this is mean. And this is your max. So you find your mean and max. And so your new mean and max, because you want to transform this or you want to convert this to a range of 0, 1, so this will be your new mean, right? So this will be new mean. And this will be new max. So this formula will be much simpler then. because your new max is 1, this is 0, so the whole thing is only 1, and this is also 0, right? So you can just ignore the whole part, because this means that this is multiplied by 1, right? So then this will be your formula if you're converting to 0 to 1. Now, here is just one example, and if you have like enough practice with this, then this will be very easy. For example, if you want to, let's say you have income range from 12,000 to 98,000, and you want to normalize, for example, this value into this range, right? So this is your V prime. Sorry, this is your V, original number. So your V prime, or your new value, is 60,000 minus mean, right, which is 12,000, divided by max minus mean, which is 90,000, 98,000. This is max minus mean again, right? 12,000. And then, as I said, this is only 1, because this is your new max, this is your new mean, so this is 1, and this is your new mean, which is 0. So basically, this is the value here. And if I give you like other ranges, like for example, I don't know, 2 to 5, then you have to write 5 minus 2 plus 2, right? Then that will be added to your model. But most of the time, we're converting to this range, 0 to 1, when we normalize. So what is the problem with this method? So the problem is that if you are, if for example, your future values are outside the original range, that is, for example, let's say you have a salary like 120K, then your result is unstable, right? And so that is one issue, out of bounds error, or also too big or too small values, or your outliers can cause noise. And another method, so that was about min max normalization, where you need to know your minimum and maximum values. So min max normalization depends on the minimum and maximum values, but sometimes those values are not reliable, especially, for example, if you have outliers. Then let's say, for example, the range of your data is mostly like between, most data are between, for example, let's say most incomes are between 50K to 70K, and then you have $1 million as an income. So in these cases, min-max normalization is not very reliable, because you are directly using those like max and min in your formula to get the new value. But that's kind of an outlier, that maximum, for example, maximum income. And we often use min-max normalization if your algorithm, for example, expect your like new value to be in a specific range, and you don't have a strong outliers. So for example, if I give you some numbers and I ask you normalize these into, for example, normalize like the example in the previous page, I give you maybe some salaries ranging from 12,000 to 98,000. For example, I may give you 12,000, 15,000, 20,000, 50,000, 80,000, and 98,000, right? And then I ask you, let's normalize, for example, 60,000 to this range, 0, 1. Then you have to use this formula. You use min-max normalization. If I ask you to normalize it into this specific range, and if you don't have like a really a strong outlier, so you don't have like $1 million like income here, which is an outlier. So if that's the case, you can use min-max. But sometimes we also want to use, for example, z-score normalization. So let me answer the question, what is the V value in formula represent? So V is your original value. So for example, let's say I give you some income. Let me write it here. So this could be, for example, I give you some values like 12,000, right? And then 50,000, 35,000, and then 48,000, 98,000. Sorry, 60,000, and then 98,000. So just for this, like, to save a space, I just told you let income range between this and this, because like in your formula, you only need min max and then you need the value. So if I ask you to actually normalize this value, right? If I ask you, this is your V, then this is V, and V prime is the new normalized value, right? So if I ask you to normalize this value into this range, right, and I give you these numbers, so you know the mean, you know the max, and you know that you can use min max normalization. Although in the exam I explicitly ask you, for example, using min max normalization, so I will help you with that. But the reason I'm explaining is that in in real, like, world project, no one is telling you what to use, right? So you have to know when to use which one. So for example, you have these ranges, and then you don't see like a strong outlier. You know what is the minimum, maximum, you don't have outlier, and so you can use this method. And so you can normalize each of like these values into range of 0, 1. Now here's just an example that I'm this is my V. I'm just converting like this number or normalizing this number. So I'm reducing this from mean, which is 12,000, right? So this is your mean, divided by the range of our data, which is max minus mean. This is how you normalize, minus mean, and then you divide it by the new range, but the new range is just 1 because we want to divide it 0 to 1. So this is your mean, this is your max. So this is max minus mean, which is 1, plus your new mean, which is 0. So basically multiply by 1. And basically this is the formula. This part is the formula if you want to normalize into this range. Is this clear? So let's go to the next one. Z-score normalization. So I was saying that where to use, for example, when to use min max. Now you use, for example, this type of transformation or normalization, Z-score normalization. If, for example, let's say, for example, instead of using min max, you just look at how data is distributed. So you use mean and standard deviation. So you basically use it if you have the strong outliers, right? For example, if you have income ranges between 10,000 to 80,000 or 20, like 90,000, and then you suddenly have one value like $1 million, which is the outlier. So if you have that much strong outlier, or if your distribution, let's say, is roughly normal or bell-shaped. So bell-shaped is just means normal distribution. So the idea is simple. You just want to ask, for example, how far is this value from your average. So the main point is that instead of using min max, you just look at how your data is distributed using mean and standard deviation. So here's the formula. Your V prime, or the new value, is your actual value or your old value minus mean divided by standard deviation. Now this is the formula to calculate the standard deviation. For standard deviation, I will give you the formula in your exam, and this is mainly also because there are two different formulas for standard deviation. So here you may have n minus 1, which is the case here. You can also have n. So there are slight differences, although like the final result is almost the same, is very close to each other. But here, if you put n minus 1, which is the case of this slide, if you divide this, let me show this here. So we have this formula for a standard deviation. This formula for a standard deviation. And you can see that I have n minus 1 here. Now this can also be n. So this can also be n. And it depends. So you use n minus 1, like the case in this slide, if your data is treated as a sample, and you use, for example, n, you divide by n if your data is treated as the whole population. So because we treat it as a sample here, we divide by n minus 1. You don't know the reason. I'm just I'm just explaining if you're curious to know why and what is the difference between these two. So this is representing that this data is just a sample. If it is divided by n, means that you treat your data as the whole population. So whole population, or n minus 1 if you divide your data just as a sample. So if your data is treated as your sample. Now why, if your data is treated as a sample, use n minus 1? Just because we lose 1 degree of freedom for mean. And by that I mean just when, for example, your mean is fixed, then one, for example, data value is no longer to change freely. That's why we lose 1 degree of freedom. But if, for example, if your data is treated as the whole population, then divided by n. In any case, in the exam, I give you the formula, and most probably this formula. So this is the formula to calculate the standard deviation. And then if this is after you actually calculate your standard deviation or the distance from the mean, then your v prime is calculated by this formula, which is v minus mean divided by SA, or standard deviation. So you have to know the mean and the standard deviation for this formula. For example, so let's see an example. So let's say mu is mean and sigma is a standard deviation, and let your mu be, for example, 45,000 and your standard deviation is 30,000. So using z-score normalization, for example, in the exam, I ask you using z-score normalization, what would be, for example, the value of 60,000? Or I may even ask you, I may give you like several values and asking you to normalize all those values. So if you want to, for example, normalize value of 60,000, salary of 60,000, based on z-score normalization, right? You have to use this formula. So your v prime, or your new value, is your old value, which is v. So this is your v, which is 60,000, minus your mean. So you have to know what is your mean, which is, for example, 45,000, divided by a standard deviation. So we also, you may also in the exam, you may also need to calculate the standard deviation. So I may not give it to you. So for simplicity in this example, I also provided standard deviation, but in the exam, you may need to calculate this yourself. And then this will give you the new value of $60,000, or let's say the normalized value of $60,000 using z-score normalization. So there are some advantages for this method. So for example, useful when actual mean and max are unknown. Of course, if you don't know what is your mean and max, you cannot use mean max normalization, right? And also I said that, for example, mean max is, for example, useful if you don't have strong outliers. But if you have, then this is more useful and better deal with outliers than mean max. And the reason is because you have, like, you're calculating mean and standard deviation, right? And so this is more useful. And then finally, we have normalization by decimal scaling. This is the simplest formula. So your v prime is your value, or vi, divided by 10 to the power of k. Now, what is this k? K is just, let me annotate again. So this k, so this value, or k, is, for example, let's say you have to see what, you have to choose k in a way that your new value, or your v prime, fall between, for example, -1 and 1, or let's say the absolute value of vi should be less than 1. Now, for example, let's say the largest absolute value is 986, right? So this is, I'm talking about the absolute value. So the largest absolute value is 986. Now, dividing this by 1000 is enough, right, to give it the result as, so v prime I is, if you divide this 986, right? If you divide this by 10 to the power of 3, which is 1000, right? So which means 986 divided by 1000 give you a value between -1 and 1, or less than 1, I mean, right? Or the absolute value is -1. So if you divide it by, let's say, 10 to the power of 1, right, your value is greater than 1. If you do it to 10 to the power of 2, is still greater. So the reason that we choose K3 here is because, or simply, you can say that, okay, this has 3 digits, right? Because it has 3 digits, dividing by 10 to the power of 3 guarantees that all your value, like your new value, is less than 1. And this is, you use it mainly when you just want to normalize your values quickly. So that just because it is really fast and quick. So if you have, for example, your data has a very large magnitude, like thousands or millions, and when you want something like cheaper than min max or z-score, and you just want to quickly normalize your data in early, let's say, data preprocessing, this is very helpful. And so do you have any questions for this? How to know what chi is, and when to use different types of normalization? Do you have any question here? Any question? Okay, so I assume that you have no question here. And so let me remove this, and I think we're done with the slides. Unfortunately, we do not have, because these topics are very important and you most probably have questions in your midterm. I didn't want to rush just finishing the slides for doing Kahoot before explaining them in deep. So just wanted to make sure that you understand each concept. And so if you have no questions, the class is finished. I will, I think, do the Kahoot next session together with the hands-on. And that's it. Do you have any question? So your midterm most probably cover, so today is January 26th. So we still have, let me also stop sharing my screen.
Is it going to be like before or after the break?
Because we still have at least 2 or 3 sessions before, your midterm. It means that I'm most probably I will be able to cover decision trees as well. So in that case, I will cover everything that I include everything that I covered so far, like introduction to data mining, data preprocessing, including all the techniques that I mentioned: data cleaning, reduction, transformation, and so on, and also decision trees. Now, there is a high probability of shifting your midterm exam to after the reading week. There are 2 main reasons for that. First, a few students asked me to shift the midterm to after the final exam, to after the reading week. But more importantly, because I want to make sure that you have enough time to study and prepare for your midterm, especially like if I'm going to cover, for example, let's say decision trees, even if I shift the hands-on session to later time, and I start, for example, decision trees next week, I would still prefer that you have enough time for practice. Ideally, I want to show you some sample questions, have at least one session with like sample midterm exam questions with you to practice. So if we want that, I think it is better to shift the midterm to after the reading week. That said, I think I will create a, just to make sure that I would like to incorporate the majority of class opinion. So I may just use a quick poll to ask whether, to decide, to just see if most students are more prefer, for example, after reading week midterm or before that. Yeah, just to, because a lot of us already have midterms already next week. Yeah, that makes sense. I already have a midterm exam for my other course before reading week, so the ideal case for me was that it would have been before reading week, because then I could put all the midterm exams in one day. But I also understand that the students need some time to practice, and yeah, I also think doing a poll is a good idea to just see what most students prefer. I think that's more fair. What when do you think would A1 be released plus 2? Your assignment 1 honestly is ready, but your assignment 1 that I prepared is on decision trees, which I've not covered yet, and I wanted to uh, include another assignment as assignment 1 on data preprocessing, which unfortunately couldn't finalize it yet. So I hopefully can do it by the end of this week. But don't worry, I'm giving you enough time for your assignments. Yeah. Do you have more questions? We are voting for that. I think. Yeah, we can. Can I use polling right now to see what majority of people thinking? Do you want to do it now? Do you want to like take the poll right now? If we do the midterm before reading week, do we still get the practice section? I'm not sure if we have time for that then, because I need to finish decision trees, and my priority is to spend enough time on each topic to make sure that you learn, and we have, for example, enough practice before moving on to the next one. I know that you may not have enough time, like with like especially those of you taking like many courses. It's important that you learn at least like most of the content in the class. That would be, I think, the ideal case for you, so you would spend less time outside class. So no, we will have a final exam. We should have a final exam. Okay, I'm going to use poll midterm exam date ECS 4412. Okay, so now I'm going to share this with you. So can you see the question? Can you see the poll? Okay, it seems like most of you are February 25 so far. So 27 of you participated, 28. So there are still 2 more students should answer this. Will you do a poll with the other section too? Yes, of course. Sharing the results with you. So can you see the results? So 50% of class chose Wednesday, February 25. 32% chose February 23. So in general, 82% of class chose after reading week. Yeah, after reading week, with only 18% of class choosing this. Now I'm going to run the same poll in the other section this evening, and then just share the whole result with you later. Is that okay? So because we also have to see what other section decide. Although your exam will be during your regular class hours, but still I would prefer to hold the exam in the same day, and that's why I'm waiting for their voting as well. Okay, so do you have more questions? Okay. Thank you everyone for joining the class today. It was nice to meet you online, and have a great day. Bye bye. Take care.